Sasa unaweka data on.
Sio meeting ndio.
Meeting la msomi mnasoma?
No wonder.
Sasa umeomba credit ya nini na unajua tu acha kujifanya.
Siko najua.
Alikuwa niita meeting.
Na watu wengi yake wamejoin hivyo.
Watu wamejoin ama yuko?
Juu.
Ngoja.
Walikuwa wanafundisha physics then wakaacha. Sijui aje.
Ama yuko? Ile yuko.
Tena angalia.
Wewe ngoja. Hapo kama ku create kutafuta hata nini kutafuta sana moto. Na hiyo kwa hiyo gorogoro.
Siko tu hapo.
Yo, fellow, turn off your mic.
Please mute.
Hello
bye.
Imetosha, weka makaa.
Hello.
Weka tu makaa.
Yo, fellow, turn off your mic.
Wakabila.
Lazima mic. Hello, sorry ba. Naipeleka kwa switch.
ilikuwa physics.
Teach. Teach.
Is there a lesson?
Can you hear me now?
Hello, acha ujinga.
Now, I initially started sharing. So let me go back. I'm having challenges here, but I'm hopefully will go. Can you see what I've shared?
Yeah.
Yes.
Okay. Okay. So I was explaining that where I started. Let me go back because of the topic is X-rays. The objectives are we need to be able to explain production of X-rays, state the properties, the dangers, the uses, solve a few numerical problems. Content, we're going to look at production of X-rays, energy changes, properties of X-rays, and under property of X-rays, we also look at soft X-rays and hard X-rays, dangers of X-rays, uses, and a few problems. And then I went ahead to show X-rays were discovered by that person there, the year, that is the history of X-rays, and why they were called X-rays at that particular time, and the production. So I'd gone, so we were looking at the X-ray tube. I hope we are all seeing the X-ray tube. Now, I was saying that the X-ray tube is surrounded by lead. This one here. I don't know whether you can see my pen. So I'm talking about this part here. This is the X-ray, this is the section which is covered by lead all that part. That is the X-ray tube. So the outside part is shielded using
I don't.
Is the lesson ongoing? I cannot hear a thing.
Yes, it is ongoing, but the teacher is not there.
Yes, Wakayo.
Christopher. Kiflami. Bone.
Mtanzania dada.
Wase kuna ligi.
Cheza peke yako.
Manura na Tanzania.
Can we all see what I have shared?
Madam, it's visible. You can go ahead now, please.
Now, there is on my side is indicating host disabled participant screen sharing. I think that's where my problem is.
Okay, go ahead now. You are the admin. I've made your co-host.
Huh?
You can go ahead now. You are a co-host.
Okay.
Yeah.
Can we all see what I have shared on the screen? Now, I was explaining about the X-ray tube. And you can all see the X-ray tube. I showed which part. Now, I was indicating that you must be able to label the parts of the X-ray tube when required to do so. You can see the tungsten, the copper, oil in, out, cooling fins. Those are cooling. Then we have the electron beam. We have the heating circuit. We have the transformer, which is a step-up transformer. Later on, you look at that. Then we have focusing anode and the filament. Now I'll go straight to, we are going to look at, now let me take you back to the tube let me explain using the tube. How are X-rays produced? Why I was asking about the cathode ray topic is because we must combine the cathode ray tube and then the X-ray. From cathode rays, you are informed that, or what you learned, I want to believe, was that when the cathode is heated, electrons are produced, and those electrons are what we are referring to as cathode rays. They travel to the anode, or they travel to the anode. Now, for the case of X-rays, when those cathode rays or electrons hit what we are referring to there as the target, in this case is the tungsten, then you'll end up with X-rays. So we are looking at fast-moving electrons which are suddenly stopped. When the fast-moving electrons are suddenly stopped, then we end up with X-rays. Now, the metal used as the target, in this case, is tungsten. There's another type of metal. It must be of a high melting point because the amount of energy being produced when the electrons are suddenly stopped is very high and can melt. So therefore then, let me now take you to the note. So when the cathode is heated, you can see there, And there are two methods of heating the cathode, by the way. We have thermionic and photo. Photo will deal with it later. Thermionic means you're using heat energy to heat the cathode. Electrons are produced at the cathode. Those electrons are accelerated towards the anode. And the anode in the tube is the target. When they are accelerated towards the anode, then they are suddenly stopped by the target. What you end up with is X-rays. If you look at, let me go back to the diagram. I'll keep on taking you back. If you look at the diagram, please ignore this focusing anode. That's not the focusing anode, but that is the cathode. Now, when electrons are produced, the anode is this where we have the tungsten. The diagram is wrongly labeled in that case. Sorry for that. Now, we have the tungsten, which is acting as the anode. And I've said the tungsten metal is a metal of high melting point to prevent it from melting. Only 0.5% is converted to X-rays. The remaining, that is 99.5% is converted to heat energy. That is why we need the target to be a metal of high melting point so it does not melt. Now, if you look at the shape of the cathode, I will do something here. This is the focusing cathode, not anode, please. That should be the cathode. Now, if you look at the shape, it's concave in shape. Why is it concave in shape? That is what I want to explain.
Allowed to focus the electron beam on the target.
What?
It's concave to focus the electron beam onto the target.
Now, I was saying the cathode is concave so as to focus the electron beam to the tungsten. That is why the shape is concave. Now, the cathode at the same time is coated with oxides of low work function. What do we mean by low work function? Minimum amount of energy required to eject electrons. So, what is coating the cathode are oxides of metals of lower work function so that electrons are easily ejected from that metal surface when the cathode is heated. Now, the anode, which is the target, as I've already indicated, is of high melting point to withstand a lot of heat which is generated, and I've indicated that the amount of heat generated is around 99.5%. That amount of heat needs to be, the target needs to withstand it. That is why we are using a metal of high melting point. Whoever is playing music behind the scenes, can you please mute your Jonathan? Jonathan. Now, the next part, so production of X-rays still. Anode is made up of a good conductor of heat. If you look at, let me take you back again to the diagram. If you look at that diagram, the side of the anode, we're having copper, we're having oil in and out, and we have the cooling fins. That is to take care of the high amount of heat generated at that point when X-rays are formed. So we are saying the anode itself is made of a good metal conductor, which is copper, which is efficient in dissipating of the heat. We also have oil, which is in circulation, which is also for cooling. And then we have the fins also. All that, the metal of good conduction, the oil circulation, and the fins are all for one process, to cool. And then what I had shown you earlier, we have lead shielding the tube. I had indicated the shaded part is lead. Why are we using lead, or why is lead being used as the shielding material? Is because lead has got high density, and therefore that will prevent X-rays, any stray X-rays, from straying outside the tube. Remember, any exposure to X-rays can be harmful if not well handled by a professional. Now, I said why the cathode is concave. Somebody's taking me back there. Why the cathode is concave is for focusing the electron beam to the tungsten. Remember, the electrons must hit or must collide with the tungsten for there to be X-rays. So why it is concave in shape is to direct or to focus the electrons there. Now, I was indicating that lead is used as a shielding. Why? Is because it has got high density, and that can prevent any stray X-rays from going outside the tube. Now, that is the old type of X-ray tube. Now, nowadays we have a modern type of X-ray tube where the target, instead of it being stationary, it rotates. Why is rotating important? To reduce the wear and tear. If the electrons keep on eating at one particular point, the target will wear out, and therefore you'll have to do replacement. So it is rotating so that you have uniform wear and tear of the target. And then the target also is set at an angle. If you look at the diagram, let me take you back again. If you look at that diagram, the target is slanting. That angle is 45. So why 45? Why an angle of 45 degrees? Is to direct the X-rays out of the tube through the window. Again, back to the tube, with the diagram, there's this window here. Just a moment. So the target, this window here, the target is this one here, which is placed at an angle of 45, so that when the X-rays, which are these ones, these are the X-rays, they are able to be directed to the window. These are electrons, stream of electrons, which in terms of cathode rays, you are indicated, you were in the, when you are covering the topic, the CRO, cathode and the CRO, you are told that these are the cathode rays, the stream of beam, the stream of electrons. Up to that point, is there any question? You can write, I will answer when I read. So this is the diagram of the modern X-ray. You can see it has a rotating anode. It still has got lead shield around the tube. Now, there's one thing I never mentioned. Let me go back to the tube again, the original tube, that is the old type of model. That tube, you can see we have a vacuum. It is labeled there, vacuum. Why is the tube a vacuum? Remember, during the production of the electrons, they are supposed to travel from the cathode to the anode. If they collide with any other material in between, there are two things which might happen. The electrons might not arrive at the target, or they will lose the energy and not arrive. Yeah, definitely they will lose some energy and not arrive at the cathode. And remember, we need the electrons to arrive at the target so that X-rays are produced. So the tube must be a vacuum so that there is no collision with any other particles, which can lead to the electrons losing kinetic energy. I think I've talked about anything, almost of the filament definitely is heated, electrons are produced. I've talked about why the cathode is concave, and I indicated, please, this is a focusing cathode, not focusing anode. My diagram at that point. So we were at the modern X-ray tube, which rotates. The anode is rotating, and I've indicated why it is rotating is to reduce the tear and wear. The tube, the glass tube, is still evacuated. We still have lead shield, and there must be a reason why lead is used. Yeah, I want to believe up to that point. Now, with the next part, I will try to move a bit fast because there were challenges at the beginning of the lesson. Properties of X-rays. So we need to cover the lesson, the topic. So properties of X-rays, they are listed there. They travel in straight line at the speed of light in a vacuum. X-rays penetrate substances, affect photographic fields, ionize gases. What do we mean by ionizing? Is they knock off electrons. When you knock from material, you cause, especially air molecules, you cause ionization. And therefore the gas ends up having both negative and positive ions. They can cause photoelectric emission, fluorescence, they cause some substances, certain substances to fluorescence. X-rays are not charged, therefore they'll not be deflected or not be affected by magnetic or electric fields. X-rays can be diffracted and plane polarized. At this level, we don't deal with plane polarized, we look at diffracted. Remember the properties of waves, and diffraction was one of them. And definitely they obey the equation E is equals to HF. That is the energy equation. Now, Since we have covered the production and we have covered the properties of X-rays, let's move on to types of X-rays. Types of X-rays. There are two types of X-rays, hard and soft. Now, what do we mean by hard X-rays? Or why are we classified certain X-rays as hard and others as soft? Now, hard X-rays have high frequency or they have short wavelength. Hence, they have high penetrating power. Now, how are they produced, or how do we produce hard X-rays? When the potential, when the accelerating potential between the anode and the cathode is high, leading to the electrons moving with a very high speed, then you end up with what is hard X-rays. That leads to production of hard X-rays. Let me repeat. When the accelerating potential between the anode and the cathode is high, that leads to electrons moving with a high velocity, and what you end up with is hard X-rays. I hope I'm clear. That is how hard X-rays are produced. The potential, the accelerating potential between the anode and the cathode must be high. When it is high, the electrons travel at high velocity, or the electrons are accelerated towards the anode, and then you end up with hard X-rays. Okay, now for soft X-rays is the opposite. How are they produced? When the accelerating potential between the anode and the cathode is low, leading to the electrons moving with low velocity. What you end up with is soft X-rays. Okay, so soft X-rays are produced by electrons moving at lower velocity compared to those of hard X-rays. This is achieved by lowering the accelerating voltage. I've already explained that. The moment the accelerating voltage between the cathode and the anode is low, then you'll end up with soft X-rays. The soft X-rays can be used to treat or to show malignant growth. But that is just a moment. Let me see what this person is saying here.
Madam, can we take a roll call?
Okay.
Okay. So check on your screen, students. Take the roll call. Pick your class and then submit. But also note that this gentleman called himself Jackson. There was also Hilary Orina. I'm getting information about your actions when the teacher was not in class, and you're following up that one by one. We'll get to hear from you. But respect must be maintained. Other students are here seriously to learn, that's all. It's 183 now. Anyone remaining? Done with the roll call shortly. It's 183 now. 187. This should take you less than 5 seconds. And those ones who said they can't see, just leave it. We have the record of the others. At 190, I think. Remember, this is the record we share with your parents to confirm your attendance in class. So it's important that you participate on that. All right. Thank you. I think, Madam, you can proceed now.
Okay, so somebody's asking, I repeat, I don't know what to repeat. We are making notes. I don't know what you want me to repeat. Please be specific when you want to say, I repeat. So I am at intensity of X-rays. Now, let me explain something here. When the heating current is high, that means more electrons are going to be produced. If the heating current is low, then that means a few electrons are going to be produced. So that's why we are saying the intensity of the X-rays is controlled by the heating current. The more the current or the higher the current, production of X-rays, okay. Now, the greater the heating current, the greater the number of electrons being produced, hence more X-rays. The lower the current, that means less the number of electrons will be produced, and therefore the amount of X-rays will be produced will be also lower. Now, to give more intense beam of X-rays, the cathode is made hotter, that is high heating current, to give more electrons, leading to more X-rays. Now, the strength of electrons, of X-rays, the strength of X-rays depends on the accelerating potential. Remember, I have talked about hard and soft X-rays. Those are the strengths we are talking about here. So that depends on the accelerating potential. If the accelerating potential is high, then you'll end up with hard X-rays. If the accelerating potential is low, you'll end up with soft X-rays. So that's what we're talking about. The strength of the X-rays depends on the accelerating potential difference between the anode and the cathode. Now, let me take you back before I look at the applications. Somebody has asked about the I repeat production. I'm taking you back to the diagram. I said during the production of X-rays, electrons are produced at the cathode. Then they are accelerated towards the anode. And I said, specifically listen to my statement, that the electrons are suddenly stopped. When electrons are suddenly stopped, what you end up with is X-rays. So production of X-rays here, we will say, just a moment. So electrons are emitted. X-rays are produced when fast moving electrons are suddenly stopped by matter. X-rays are produced when fast moving electrons are suddenly stopped by matter. That is in the diagram. So when the electrons traveling from the cathode are suddenly stopped by the target, what you end up with is X-rays. I hope I've answered the person who was asking me the question. What is the function of the step-up generator in the diode? It produces current. That's where we get our current from. And as I say, step-up transformer is not for at this level. You're going to cover it on its own topic. So don't get worried here. Okay, yes. So let's move on then to applications. You have looked at intensity. You go to applications of X-rays or uses. In medicine, please ensure that at least you know 2 uses or 2 applications, and you can clearly explain the application. So in medicine, normally if if a physician suspects that you have a fracture, they normally send you to go for an X-ray. So in medicine, you'll go for an X-ray, they'll take the photograph and they'll be able to. So due to penetrating property of X-rays, fractured bones or dislocated joint can be seen from the X-ray photograph or radiograph. If you happen to swallow foreign objects or like children playing, hard X-rays can be used to treat cancer, cancerous tumors. In science or the study of crystal structures, which we refer to as crystallography, you can use X-rays, study of crystal structure, which explains the arrangement of atoms in different materials. You can use X-rays, or X-rays are used to do that in the industry, especially in manufacturing. Like now, where factories where Mabati iron sheets are prepared or are manufactured. For them to check that what they are giving to their clients is of high quality, they do not have cracks or flaws, then X-rays can be used to sterilize. In a security at the airport, normally your bags are checked as you go through, even yourself. If you have hidden weapons or whatever. And then dangers of X-rays. This part you must be able to explain. Combining your biology, you can come and explain what are the dangers of X-rays. Now remember, when X-rays penetrate matter, remember one of the properties we say they cause ionization. And therefore, what happens when somebody is exposed to X-rays, and especially in large quantities, there can be damage to the body cells. That is excess exposure to living tissues that can lead or kill the body cells. So normally that is why you are always, there's always a caution on exposure to X-rays. You're not supposed to be exposed. You don't go for X-ray now and then, no. It is when it is unavoidable. X-rays can also cause genetic changes if one is exposed to them, and can also cause cancer. That is why there should be limitation to exposing, not for a long time, and again, when. Now, precautions when using X-ray machine. The machines are normally surrounded by lead shield and are already indicated why. Why it's surrounded by lead. Why lead is used? Why specifically lead is used? At the same time, the rooms, the walls normally are, I think, double wall, concrete walls to prevent any stray X-rays going to the outside, and also the time of exposure is reduced. Must be exposed, if you are to be exposed to X-rays, it must be within a very short time. Somebody is telling me there is MRI scan. My friend, not everybody can afford MRI scan. X-rays are still there. And it's from the study of X-rays that any of those has come. So you cannot talk about, we can't do away with what has already existed. It is already there. It has the one which has been improved. So, and you find that X-rays are cheaper than MRI. And I want to believe we are all Kenyans and we understand. Okay. Energy of X-rays. This is where I want you to pay attention again. Remember last time when I was looking at electromagnetic induction, we looked at the equation of energy, E is equals to HF, where H is a Planck's constant and F is a frequency. That equation is very important. And I want to believe when you're looking at cathode rays, although when I was trying to ask what you covered, you did not explain, you must have come across a few equations which can be used. And all those equations are sometimes related. You will find yourself using it in X-rays and at the same time using them cathode rays, or when you're working with the electromagnetic induction, electromagnetic spectrum. So these are the formulas. Energy can also be equal to electron EV, electron volt, where E is the electron charge, which is normally 1.6 times 10 raised negative 19. And then V is the accelerating voltage. In one way or another, as I have indicated, these equations are related. So you'll have to look at when required to use which equation will I use at this particular point. Before I go to questions, any question, because up to that point, we are through with the topic of X-rays, unless somebody has got a question. If you have a question, please write on the chat so that I can respond at this point before we look at a few questions. Before we close the lesson, we come to the end of the question. Any question? Anybody with a question? Yes. How do we apply the equation? Yeah, that's what I want us to do. I want us to go through a few questions and see where to apply. Oh, the equations, let me. The equations are still on the screen. If E is equal to HF, And we go to form two waves where speed of light is equals to frequency times wavelength. Frequency is also equals to that. And therefore, at that point, energy can be what you have there, Planck's constant times speed of light divided by wavelength. And then I went ahead and said energy also can be calculated using EV, where E is the charge of the electron. It's normally a constant, so you'll be given that. So, but I said it is 1.6 times 10 raised negative 19 coulomb. That's the charge of an electron. And then V represents the accelerating voltage. That is the equation there. Please ask questions related to X-rays. That is the X-ray topic at this point. If there are no questions, so can we look at a few questions, especially where to apply the equations that I have shared up there. So number one, you are to calculate the, can we work out question one so that we give us, you give me answers? Applying, calculate the wavelength of X-rays whose frequency is given that. That is the frequency. Remember, speed of light is a constant. It is given there, 3.0 times 10 raised to 8. Planck's constant is also a constant given there in case you need to use them. But for question one, you don't need. Which equation are we going to use? Okay, I can see somebody here. Can I have more answers? C is the speed of light. If you were in the last lesson that I covered electromagnetic spectrum, I explained what C was. Unless you were not there, I said C is the speed of light or the velocity of light. Anytime you come across C, that you know it is the velocity of light, not just any other velocity, but velocity of light. I can see somebody has given an answer here. What are the units? We are forgetting units. We are forgetting units. So we are using this equation. Somebody was asking me, how do we apply the equation? We are using this equation, this one here. That's the equation we are using. C, you have been given. You have been given the frequency. You're looking for the wavelength. I'm still waiting for more answers from you. Answers from you. Include the units. Include the units. So the answer is 1.5 times 10 raised to negative. Let's move on to question 2. Question 2, find the energy of the X-rays whose wavelength is that in a vacuum. Question 2. I can see one person has responded. Is it negative 16 or negative 15? Let's work out our powers properly. Our powers. Let's get more answers. Remember, we are using the formula. We are using the formula E is equals to HF. E is equals to HF. The equation E is equals to HF. You have to get your wavelength. You have the frequency. You must combine two questions. Because what you have is wavelength, so you must get frequency. I think that power should be negative 15, not negative 16. Okay. The ones who are writing 16 are 19 points. Always simplify your answer. You know, when you're writing in standard form, how you're supposed to do that. Now, I want to take you to another type of question, not calculation. We have a diagram there. Let me. This is focusing cathode. So we have been asked there, briefly explain how electrons are produced by the cathode. Briefly explain how kibiwatt titers, yes?
The electrons are produced at the cathode, and then they are transmitted to the anode, where the electrons are suddenly stopped, which leads to the production of X-rays.
We have, the question is briefly explain how electrons are produced by the cathode. How electrons are produced by the cathode. The production of electrons at the cathode. It is by what? Thermionic emission. We are heating the cathode. Okay, keep it what?
Yes.
Now, are the electrons produced and accelerated towards the anode? We have already talked about how the production. The acceleration is by creating a potential, by ensuring that the accelerating potential between the cathode and the anode is different. That will make the electrons be accelerated. Why is the target made of tungsten? Why is the anode made of the tungsten? Can somebody give us that answer?
Penetrating.
Yes, heating you still get. If you say by heating the cathode, you still get a mark. But it's good to say thermionic, because we have two types of heating. You can have photo and thermionic. You need to differentiate between thermionic emission and photoelectric emission. Thermionic emission, you're using heat energy. Photoelectric emission, you're using the radiation. Okay. Oh, why is the target made of tungsten? I was waiting for that answer. Somebody? Why is the target made of tungsten? Which other metal, by the way, is used other than tungsten? It has a high melting point. Yes, because of its high melting point. Somebody is writing here to prevent the X-rays from penetrating. No. It's because why the target is made of tungsten, because tungsten has got high melting point. As I explained earlier, remember the heat energy is 99.5%. So that heat energy needs to be dissipated. If it is not, it will. So that is why the tungsten must be a metal of high melting point. And then, how is cooling achieved in this kind of X-ray?
Really?
How is cooling achieved in this kind of X-ray machine?
Oil in, oil out.
Nimrod, yes?
Cooling is provided by the cooling fins on the outside of the tube and the circulation of oil through the channels in the copper block.
And then? And also the copper. The anode is made of copper. There are three ways of cooling, how cooling is achieved. And then we have, why would it be necessary for the target to rotate during operation?
To prevent
Why? Yeah, two people have raised their hands. Let me just see. There is Griffin Mugambi.
To prevent wear and tear.
Yes. Not okay, not to prevent. You can't say to prevent. There will always be tear and wear.
Reduce.
To ensure that it is what? Uniform.
Uniform.
Yes. So that you reduce the time of replacing the anode. Just a moment. I want to see if there's another question. Other calculations. So up to that point, I want to come to the end of this lesson. Please go through again as you make your notes. Definitely go through, try to internalize what you have covered and make your notes, include what is not there in your book or what maybe. And when you're making your notes, please use more than one book. Don't just rely on one book. Up to there, I want to stop sharing. I wanted to ask, I know there's a part of cathode rays which remained. And Mwalim indicated that we will see whether we can cover it. But we'll cover, the remaining part is a small bit, we'll cover it during our normal lessons, but when we are back in school. Just remind your teachers in your classes. Okay?
Yes.
Have a good day. Now, I can see there's somebody here.
Bye.
I share how? Somebody saying I share notes. After the lesson,